Right, so reversible reactions and dynamic equilibrium, right? Reversible reactions are reactions which can go forwards and backwards at the same time, all right? So there, if you have an example of A plus B reactants going that way to produce C plus D, then spontaneously the products C plus D can also react with each other to go back to becoming the reactants. All right. And these two reactions, the forwards and the backwards reaction, can happen at the same time, all right, as the amounts change. So from that, we have an equilibrium position, which is defined as the point at which the amounts of reactants and products stop changing. Okay, that implies that the forward reaction rate of reaction equals the reverse rate of reaction. Okay, right. Using a particular example, the Haber process is the one that usually comes up in the exam, if it does at all. It's what we use to produce ammonia, all right? So you'll have nitrogen gas added to hydrogen gas to produce ammonia. And this one is also gases, all right? So, excuse me, what happens with this is that there are some details of the reaction that will be given in the exam questions, which you need to know in order to understand what the equilibrium position is. So first of all, this particular reaction, yeah, do you remember, is it endothermic, exothermic? Any idea?
Is it exothermic?
It is, yes, well done. So this thing, first of all, is exothermic. All right. And that means it gives out energy in the form of heat during the reaction. All right. So when it gives out energy during the reaction as heat, as it were, the surroundings, i.e., if there's any solution or the air around it, is going to heat up. All right. So the whole thing heats up. And I should put that in specifically. Okay. Right. Now, in this case, for a set of given conditions, right, of pressure, temperature, and concentration, for example, it will achieve a certain level of equilibrium, right? At a point where there'll be a certain amount of nitrogen, certain amount of hydrogen, and a certain amount of ammonium present. So the ammonia is going to be present along with the reactants. All right. If we change any of the conditions, right? If conditions are changed, then the equilibrium position also changes. This means the amount and indeed amounts of reactants and products present will change. Right? The guiding principle on this, the theory behind it, is called Le Chateliers Principle. All right. This states that when a reaction system undergoes a change, the reaction will move, if you like, to oppose that change. All right, try and create the opposite condition. All right. So in this case, let's just bring that back to mind here. So we have N2 gas plus hydrogen gas. And remember, this one was exo in the forward direction. Right? So this is the exo side. If the reaction is reversed and it goes in that direction, then this is the endo side. Endothermic in that direction. Yeah? Okay. So what are the effects? If we first of all look at temperature, all right? Temperature increase. If the temperature goes up, right, the system wants to reduce the temperature again. All right? So from what you see there, which direction do you have to go in to actually cool things down?
The backwards.
Right. Okay. So for that to happen, reduce the temperature again, the reverse reaction rate increases. So in other words, it moves in the endothermic direction. All right, does that make sense so far? All right.
Yeah.
So it moves in the endothermic direction, etc. So as a result, right, what is the net effect of that? Is that there will be more reactants than before. less of the products. All right. So effectively, in this particular example, right, if you increase temperature, the reaction moves in the endo direction. Okay. There. Okay. All right. Then we could talk about, for example, a pressure change. If the pressure increases, the reaction or the equilibrium position will move in direction that has fewer gas moles, right? Fewer moles of gas. All right. Let's remind ourselves. In this one, you've got 1 and 3, 4 moles of gas on the left-hand side in the reactants, and only 2 moles of gas on the product side, on the right-hand side. Yeah? So, as a result, if you increase the pressure, all right, this particular reaction is going to move to the right, and it will produce more of the reactants. All right. That is a standard rule. Always goes to the side with fewer moles of gas. If there were any solids in here, for example, right? If there are any solids, they don't count. You only look at the moles of gas on both sides. All right. So again, reiterating that, you've got the pressure increases and the equilibrium moves towards side with fewer gaseous moles. All right. Does that make sense so far?
Yeah.
Okay. And the last one that's relevant in this is changes in concentration. All right. Concentration increase what the system wants to do is wants to reduce the concentration of a particular substance. Okay, back to what it was before. So it wants to oppose that increase. All right. So if I were to, for example, in that reaction, increase the concentration, like maybe packing things into a smaller volume of the nitrogen or add more nitrogen, then the system wants to say, okay, let's use up that nitrogen, extra nitrogen, bring it back down to the level it was at before. All right. So it's going to then try and react more of that nitrogen down and produce more ammonia. All right. So again, what it'll do, it will move to the other side of the substance whose concentration has increased. Okay, so it means away from the higher concentration. Okay, all right. So that all right. Does that all make sense so far? Yeah. All right. So now looking at the type of questions that you get, I mean, if you get an equilibrium type question, more likely than not, it'll be Haber process related. You could get something else, but like I said, it's more likely to be this type of question. All right. So as a result, the three things, if you were to combine them in different ways, you let's just run through that again, all right? Just to explain what I'm trying to say. So if you were to increase the temperature, it moves to the endothermic side. If you were to reduce the temperature, it would move towards the exothermic side. All right. And depending on which way the endo-exo is, that will determine whether you produce more of the products or you reduce the amount of products produced. All right. With pressure, it's straightforward. You literally count up the moles of gas on both sides in a balanced reaction. It's got to be the balanced reaction equation. Count up the number of gaseous moles in each side. Whichever side has the fewer number of gas moles, that's the direction it'll go in if you increase the pressure. If you decrease the pressure, then it'll obviously go towards the side with more gaseous moles. All right? With concentration increase, if you increase the concentration, then it'll want to move away from it and go to the other side of the equation. Right? So you produce more of the other side. And if you decrease the concentration, then the system's going to try and fill that gap and try and make more of whatever it is that you've messed around with and try and come to this side again. Right? When I say this and that, I'm being a little bit vague deliberately because different reactions, obviously different equations will have different behaviors. But these principles always apply in any of the dynamic equilibrium. All right. And this whole system, right, is called dynamic equilibrium. Because it can change and even at equilibrium, the reaction has not stopped. That's a common mistake in the exam questions, right? Or answering exam questions. The reaction has not actually stopped. Both forward and reverse reactions are still happening at the same time, right? So both forward apologies. Reverse reactions are happening at the same time and at same rate. All right? That's why it appears to have stopped. All right? Does that make sense? Yeah? All right. Any questions on that? No? All right then, okay. If we need to add in any other conditions of the reaction, then just let me know and I'll add to that if you wish. All right? Okay, cool.